In this part of section 13.3, we're going to define some other vectors corresponding to a curve similar to the unit tangent that we already have. Though we'll kind of start with the unit tangent to do so. So we'll say we have a curve C and some parameterization R of t. Recall our unit tangent is given as capital T of t is equal to R prime of t divided by its magnitude. And now we're going to make use of one of the properties of this unit tangent. Specifically, that it is a unit tangent. The magnitude of t of t is always equal to 1. And so we actually do have a vector valued function, capital T of t, with a constant magnitude. So if you recall from section 13.2, we noted that means that capital T of t and its derivative, capital T prime of t, are always perpendicular to each other. They're always orthogonal. That means that capital T prime is actually always perpendicular to the curve at every value of little t. We call a vector that is perpendicular to a curve or even to a surface, we call such a thing a normal vector. So we're going to talk about a normal vector to our curve. Now, there is a slight issue here. T prime of t may not be a unit vector. So, sort of like we did with the unit tangent, we're going to make a unit normal. We're going to call it capital N for normal. As you can kind of tell, the t here was for tangent. Here N is for normal. We'll have another one that'll have a standard letter as well, but we'll get to that. This is going to be the derivative of t divided by its magnitude, just to turn it into a unit vector. Now, this is actually a particular normal vector. There are multiple unit normal vectors to a given curve, and by doing this, we've actually picked out one that is the most important normal vector to that curve. But to kind of see why that is, let's actually look at an example. So here, I'm going to look at the curve R of t given by the parameterization 5 cosine t, 5 sine t. It's a fairly nice, simple example. In fact, if you remember how this works, this is just going to be the graph. This curve is actually just going to be a circle with radius 5. If I take the derivative to find the tangent, derivative of 5 cosine is going to be negative 5 sine. Derivative of 5 sine is going to be 5 cosine. I'm going to have to divide by the magnitude of r prime. But the magnitude is pretty easy to find because if we square this and add it to the square of that, we really just get sine squared plus cosine squared. That gives us a 1, and so we end up overall with a 5. So really all we're doing when we divide out by the magnitude, we're just getting rid of the 5's. So we get negative sine of t, cosine of t. If we differentiate this, derivative of negative sine is negative cosine. Derivative of cosine is negative sine. And as luck might have it, this is actually already a unit vector for any given t. We don't have to divide out by the magnitude of t prime because it's just 1. So in fact, this is just n of t. That's definitely not always going to be the case, but I wanted to make a simple example at first. Let's go ahead and plot this particular curve. So the name of our curve was R. or the function name was r. It's the curve with components of 5 cosine t. I accidentally put a space there, so it didn't recognize the cosine anymore. Then we have 5 sine of t. Our variable is t. And of course, since we are dealing with just trig functions, we're going to take the limits to be 0 to 2 pi. So a nice circle of radius 5. I'm also going to, since we're going to be looking at points on this curve, oops, don't want that. What I'm going to do is I'm going to make a slider. The slider is going to allow me to pick a bunch of points on my curve and move those around as I want to. So here I picked an A. A is going to be a parameter that I'm going to plug into my parametric curve. So a given point on the curve could be r of A. As I change my A value, it changes the point. It moves that point around. My formula for t, so t is going to be my unit normal vector, or sorry, my unit tangent vector at the point A. It's going to start at the point A, and it's going to then finish at that point plus the formula that we had for t. So our formula for t was negative sine of t, of little t, which is in this case going to be a. So negative sine of a, and then cosine of a. In fact, let's give this a different color so it stands out a little bit better. In fact, let's zoom in slightly so it stands out more. Move this up a little bit. There we go. So here, our tangent vector starts here and moves a distance of 1, which looks kind of tiny on here because this is a radius 5. But I want it the curve to be a little bit bigger than the actual vectors. As we move along the curve, the tangent vector does stay tangent to our curve at every given point, and is always pointing in the counterclockwise direction. Our normal vector, we're still going to make our vector starting at that point, but then we're going to use the formula for that we derived for that normal vector. Remember, that was negative cosine of a, negative sine of a. And again, we're going to go ahead and give that a different color. I'm going to go ahead and color it green. We'll make it a little bit darker of green. Maybe that one. There we go. That should stand out well enough. So here, this normal vector is always perpendicular to the curve. It's always perpendicular to t specifically. And as we move around the curve, as we move around the circle, it's always pointing in a particular direction. And note that there are 2 possibilities for our normal vector. We could have been looking at the vector that points outwards, away from the center. But our formula gave us the one that points towards the center. And that was not an accident. The normal vector here is actually telling us which direction we're turning. If we were to look at what direction of our tangent vector we're going to end up on, it's always in that direction of in. We're always turning towards in. And that in is actually telling us that particular fact. So as you can kind of see here, as we go around the circle, we always move towards the center. And that's what makes our circle actually close up at the end. Now, the fact that the normal vector always points in the direction that we are turning is actually still holds true in 3-dimensional space. In fact, it is a little bit more important there because there are a lot more directions that we can be normal to a particular curve. And in fact, there's infinitely many normal vectors to a curve at a given point. And the unit normal that we get from our formula is going to pick out the exact one that is the direction that the curve is turning. So let's actually look at an example. This is going to be r of t is equal to 3 cosine of t, 3 sine of t, 4t. I picked a fairly easy example here. This is what we call a helix. I changed the 5 to a 3 in this case. That's actually going to work to our benefit later on. We're going to start by finding the unit tangent and the unit normal. So we take the derivative. This is going to be negative 3 sine t, 3 cosine t, and the 4t just becomes a 4. The magnitude of r prime. So we have square root of 9 sine squared plus 9 cosine squared plus 16. Sine squared plus cosine squared is 1, so we end up with a 9 plus 16, which is 25. And so our magnitude is 5. We go ahead and divide r prime of t by 5. Now, we don't actually just cancel out all the numbers this time, but it is nice enough. We get negative 3/5 sine, 3/5 cosine, then 4/5. That is our unit normal, or sorry, unit tangent vector. It is a unit vector that's tangent to our curve. If we want the unit normal, we differentiate this again. Derivative of this is, well, derivative of sine is cosine, so we have a negative 3/5 cosine. Then we have a negative 3/5 sine. And then actually, the 4/5 just goes away. This time, this is not a unit vector already. This is it's going to be normal to the curve, but it's not going to be a unit normal. So we need to find its magnitude. So we have, well, actually, what we can do here is we can pull out the 3/5. So that'll be out in front of our square root. We have cosine squared plus sine squared. And hopefully that's pretty easy to see that that turns into a 1. So overall, we get 3/5 as our magnitude. And so the unit normal, if we divide by 3/5, we get negative cosine t, sine t, and 0. So actually, sorry, this should be a negative. I forgot the negative sign. So this is actually very similar to what we had in the previous one. Let's go ahead and plot this particular curve. All right, so we define our curve. We're still calling it R. It's a curve with parametric equations of 3 cosine t, 3 sine t, and 4t. Our variable here is t, and I'm just going to toss in really wide bounds. Actually, I could probably just do 10 to 10, negative 10 to 10. So here's our curve, or at least what we can see of our curve. Now, the fact that we do have the 4t here means that this is actually does go up and down pretty quickly. If we scale down our z-axis, we can actually see what's kind of going on here. So this is a helix. It's just going around. It's actually going around a circle of radius 3, but going up and down as it goes. Now, we don't need to actually look at this entire thing. It actually will make a little bit more sense if we keep the axes scaled the same, because when we actually draw things that are supposed to be perpendicular to each other, it will not look perpendicular if we have different scalings. So we'll just keep it in the standard view. We'll only look at this part of the curve, but that's all we really need to be looking at. Now we'll go ahead and put in our unit tangent and unit normal. So actually, let's before we even get started, let's go ahead and plug in r of a. So a here is a scalar that I've already predefined. So at 0, it gives us the point 3, 0, 0. As we move this around, you see we select different points along the curve. Our unit tangent vector is going to be a vector that starts at r of a and then moves by our formula. Remember, our formula for our unit tangent was negative 3/5 sine of a, 3/5 cosine of a, and then 4/5 for the last one. And similar to last time, I'm going to go ahead and give this a color to make it stand out. I'm going to stick with red for our tangent. So our tangent is sticking out there. It's a relatively small vector because everything's kind of scaled pretty. So our scalar is kind of pretty small here in regards to what we can actually see. But you can tell it points along the curve, and it always points along the curve no matter what point on the curve we pick. That's what we want. In is going to be the vector that again starts at r of a, then goes to r of a plus our formula for the normal. So our formula here, remember, was negative cosine of a, sine of a, and then just 0 for the last term. Oh, sorry. I dropped the negative. It should be negative cosine of a, negative sine of a. Now we get a vector like that. Again, let's give this a different color. Let's pick that value of green. So as we move along the curve, that unit normal always sticks out in a particular direction. It's actually, in this case, always pointing towards the z-axis, and it's telling us that we're always curving towards the z-axis, no matter what. So it's actually pointing in the direction that the curve is turning, and that's what we wanted to see. Now, it doesn't really actually give the full amount of information about the curve. So there is a little bit of what we could call twisting to the curve. We're not just going around in a circle around the z-axis, even though the unit normal is telling us that we're always turning towards the z-axis. We are moving upwards as well. And so we can actually define another vector. And let's go ahead and write down what that's going to be on another page. We're going to take the tangent vector t, the normal vector n, and we're going to take their cross product. Because what we're really doing here is we see that in our picture we have two orthogonal unit vectors. And we're working in three-dimensional space. In three-dimensional space, generally we like to have three different directions. We have an x, y, and the z in our normal axes. How about having an x, y, and z kind of vectors at this point? In fact, I kind of picked the colors to be that. Our x is our tangent, that's our red axis here. Our y is the green axis, that's our normal vector. And then we're going to go ahead and pick a blue vector that is a unit vector that's perpendicular to both t and n. And that's what the cross product is doing. The cross product of t and n, we're going to call that the vector b. We could actually write this using our parameters if we want to. And this is going to be called the binormal vector, because it is a normal vector to the curve. It's just not the unit normal. It's not the regular unit normal that we get from our formulas. the unit normal tells us, specifically tells us in what direction the curve is turning. This b of n, or this b of t, this binormal vector, is kind of going to point in the direction that the curve is twisting, in a sense. Now, I didn't call this a unit binormal, but we could if we want to. And we don't have to worry about it turning it into a unit vector. B is always going to be unit when we take this cross product, because we're taking the cross product of two unit vectors that are perpendicular to each other. And that will always result in another unit vector. We actually will refer to these three vectors together as what we call a frame. A frame here is essentially just saying we have three perpendicular directions that kind of play the role of kind of like the x, y, and z coordinates, like I just mentioned. That's what a frame means. But frames can move in a sense, and that's what we're doing here. We're looking at various frames along the curve. If we actually want to be more specific, this particular frame that's related to a curve is called the Frenet-Serret frame, named after some mathematicians that derived a lot of stuff about vectors with regards to curves. They kind of came up with a lot of this stuff. Now, there's actually a little bit more information that we're going to throw in here in a moment, but let's actually find the binormal for this particular curve, and we'll go ahead and depict it on our graph. So remember, b of t is just going to be the cross product of what we already have. So t is negative 3 over 5 sine of t. That's times I, plus 3 over 5 cosine of t times j, and then 4/5 times k. That's going to be crossed with negative cosine t, negative sine t. Should go ahead and put the i's and j's in here like I'm supposed to. So that's negative cosine t I minus sine t j, and then plus 0k. If we go ahead and work these out, so first this is going to be multiplied to, well, I times I gives us 0, so we don't have to worry about that one. I times j is a positive k, that's the correct direction. So we have negative 3/5 sine times negative sine, or in other words, we have a 3/5 sine squared times that k. Moving on to 3/5 cosine tj, we multiply it to the negative cosine ti. J crossed with I is a negative k, but we already have a negative there. And then the other stuff combines to give us a plus 3/5 cosine squared t times k. J crossed with j gives us a 0 again, so we don't need that one. And then we take the 4/5 k times both of these. So really we're putting 4/5 in front of both of those. We just have to figure out what are the vectors. So k crossed with I, that's the correct direction. We get a positive j, but we have a negative there, so minus 4/5 cosine t j. And then finally, k crossed with j is the wrong direction, so we get a negative I. We already have a negative there, so we actually get a plus 4/5 sine t I. If we go ahead and put these in our angle brackets, our first component is this I back here. We have 4/5 sine of t. Second component is this negative 4/5 cosine of t. And then the k's, we have two k's. Those do combine, but then we have sine squared plus cosine squared gives us a 1. So our third component just becomes a 3/5. Let's go ahead and plot that vector. So b here It's going to be the vector that starts at our R of A and then ends at R of A plus our formula for our binormal. So we have 4/5 sine of A. Then we have a negative 4/5 cosine of A. And then finally just 3/5. And again, I'm going to give this a color. And I already mentioned before that I'm going to make that a blue color. Can't really see it in this particular case, but the binormal comes off in this direction here. Maybe it's a little easier to see in this orientation. But as I move my point along the curve, we have three vectors that are defined by that curve that point in mutually perpendicular directions. All three of these vectors are perpendicular to all the other ones. But as we can see, the B is pointing in this direction, and that's telling us that we are kind of twisting in that direction compared to where N is pointing. This can actually be a little easier to see when we actually define some particular planes that are defined by these. So once we actually have these vectors, we can actually determine planes by taking pairs of them. And there's two planes in particular that we care about mostly. The first one is going to be the normal plane. This is a plane determined by N and B. So let's go ahead and plot that. Now, unfortunately, while there is a plane command that we could use here, it doesn't allow me to just pick two vectors. It'll throw an error if I do that. One thing I could do is give it 2 lines, so that's what I'm going to do first. I'm going to define 3 lines. Those lines are going to pass through my point, R of A, and they're going to be in the directions of my unit vectors. So let's maybe I'll just call this T line, just to make it easy for me. The N line is going to be the line going through R of A in the direction of N, and the B line is going to be the line in the direction, it's through the point R of A in the direction of B. Those kind of clutter everything up a little bit, so I'm not going to show them on here, but GeoGebra now knows about them so that I can use them in formulas. Specifically, I'm going to look at my normal plane. This is called normal plane. It's going to be the plane that goes through the lines N line and B line, because those are the lines that are determined by the vectors N and B. So this is our plane. And notice that this plane is perpendicular to the curve. And it stays perpendicular even if I change my parameter. As I move it along the curve, that plane remains perpendicular. In fact, this plane essentially contains all the vectors that are normal to the curve at this point. So the N and B are two specific normals that are important, but all the other normals are in this plane. Now, that's kind of all we really want to talk about the normal plane. The other plane that we're going to talk about is actually a little bit more interesting. This one is called the osculating plane. This plane is determined by the original 2 vectors that we had, t and n. So let's go ahead and put that one in here. So here, okay, it actually has a command using the term oscillating. There's an oscillating circle that we're going to talk about in a moment, but I want to actually explain what that is before we look at it. So the oscillating plane is going to be the plane that contains the t line and the n line. Now let's move the label here. So this plane, in a sense, really looks like it's following the curve pretty closely. Sort of like how it, well, it does contain the tangent. It is kind of along the curve. But as you can kind of tell, it on one side, as we go down, as our a value decreases, our curve ends up on one side of the plane, and as our a value increases, it ends up on the other side of the plane. And that's what the vector b actually shows us, where the curve is going to end up with regards to our oscillating plane. And that's what I mean by it twisting. It's twisting up out of this oscillating plane. Once we have this oscillating plane, we can actually go back to our curve and look at what the curvature of this curve actually is. Remember, the curvature is given as the magnitude of t prime over the magnitude of r prime. In fact, we have both of these now already. The magnitude of t prime was 3/5. Our magnitude of r prime is 5. So our curvature is, in fact, a constant value of 3/25 in this particular case. And the important thing about that here is if we take this number and we flip it upside down, so 25 over 3, that particular number is going to be something that we can see in our curve. Specifically, if we take the point that we are going to go out from our R of A, following the direction in with by a distance of 25 over 3. So I'm going to define a new point. I'm going to call it, can I call it O? No. O, they want O to be the origin. So maybe I'll call it capital C. Capital C is going to be the point where I take R of A, and I'm going to add 25/3 times the vector in. That gives me a point over here. It's in the oscillating plane. It's actually on the line that follows in. If I show that in line, it actually does pass through that point. But there's an important thing about this particular point. If I draw a circle, maybe I'll call the circle little c. It's going to be a circle with center C and radius 25 over 3. Oh. Since the circle is in three-dimensional space, I have to be a little bit more careful. There isn't a one circle that has the center and radius of 25 over 3. We have to define what plane that circle is in. And I can do that by giving it a vector that is normal to the plane. So in this particular case, that would be the vector b. B is actually normal to the plane. It's always perpendicular to it. And that tells us what orientation our circle is going to be in. So I'm going to go ahead and put a b there, and it's going to give me a circle. A nice big circle because it does have a radius of 25/3. But the point here is that this circle passes through our point, and passes through the point in such a way that you can almost not really tell the difference between the curve and that and that circle. Though that circle is very much just kind of telling you exactly what the curve is doing at that point. And in fact, as I move my parameter around, that will remain true no matter where I'm at. That circle very closely approximates the curve at that point. That's what we call the oscillating circle, and that's what apparently GeoGebra would be able to calculate specifically for us without us having to do all that work if we wanted it to. It can actually figure out what those oscillating circles are. I've never played around with that function. I don't know how well behaved it is, but I'd have to assume that it works pretty well. So the oscillating circle, put S there, osculating circle is a circle in the oscillating plane with radius 1 over the curvature, and should probably say in the direction of n. Maybe that's not the best way of writing that, but hopefully you get the idea from how I actually plotted it for you. But the oscillating circle is it's sometimes also called the circle of curvature, is really just telling us exactly what the curve looks like at that point. It's the closest circle that we can possibly get to approximating the curve. So you can already see here that the curvature kappa is related to our frame, to our Frenet-Serret frame. In fact, we can actually get some formulas here. So first of all, if we were to differentiate t, the unit tangent, with respect to arc length, that is always going to give us kappa times n. And that shouldn't be too surprising at this point. Remember, kappa was defined in terms of the derivative t with respect to s. It's actually the magnitude of this vector. And the n here is just telling us what direction that vector is. The derivative t with respect to s always points in the direction of n, and it has a magnitude of kappa. We can also define another function similar to kappa. This is called a torsion. It's given by a Greek letter tau. It's like a lowercase t. Tau is going to be defined to be the magnitude of the derivative of b with respect to s, though we actually put a minus sign there. That's kind of just a choice that was made in the past, but it's just we define it to be the negative of the magnitude of the derivative b with respect to s. It turns out this derivative of b with respect to s is also always in the direction of n. So db ds is negative tau, because that's the magnitude, times n. And you kind of what we're seeing there is that the derivative is always kind of pointing outward from our curve this time. There's actually another formula here. If we differentiate n with respect to s, and this one, it takes a little bit of work to actually prove, but the derivative n with respect to s can be made up of a combination of t and b. It's actually negative kappa times t plus tau times b. So kappa and tau actually show up again. The curvature and torsion are in this formula. These are what are referred to as the Frenet-Serret just formulas. And the collection of our Frenet-Serret form t and b with the functions kappa and tau, this is frequently called the Frenet-Serret apparatus, because it's all the information that we need to know about a curve, or that we can know about a curve, that will pretty much tell us exactly everything we need to know about that curve. In fact, if curves have the same Frenet-Serret apparatus, they will basically just be the same curve. up to, we could move it around a little bit. We could just translate it around. But this is the set of information about the curve that tells you everything you actually need to know about the curve. But we're not really going to get more into it than that. I just want you to know that all these are here. The video's are already gone on quite a bit of time, but hopefully at this point you have a good idea of what these functions are, what these vectors are, and how they relate to our curve. So I'm going to leave that there, and I'll see you guys in the next video.